So, now let us come to the discussion of the force. So, for our studies for this module, we will be using relatively short range force or the potential. I mean, the force you basically take by a gradient of the potential, and the potential that we shall be using for the purpose of our study is the so called the Lennard-Jones potential. Okay. And the expression of this Lennard-Jones potential looks like this. So, V of r is equal to 4 epsilon, epsilon is a unit of energy, it sets the scale of the energy, and into sigma to the power r, sigma is a parameter, I shall explain what that means, minus sigma by r to the power 6. Okay. So, so this potential looks something like this, right. So, here you have I plotted V of r on the y axis, and on the x axis is r, and the functional form of the potential, when you plot this function, it looks like very sharply increasing potential for r less than equal to sigma. Okay. So, it is very fastly increasing. After that, there is a potential minima, there is some attractive potential, this is negative here, and then it gradually goes to 0 as r increases. So, what does this potential mean? I mean, what does it signify? So, suppose that you had two particles, right. I mean, you are calculating the interaction between two particles, and they were spherical particles and of size of radius sigma by 2. Okay. So, when they were at a distance r which is greater than sigma, so each is sigma by 2. So, when they touch, suppose these are those two particles, and when they touch, the distance between their centers would be exactly sigma, and at sigma you see that the potential is exactly 0, but as soon as the distance between particles becomes less than sigma, so basically less than the diameter, there is an extremely fast increase in the repulsive potential, right. So, sigma by r to the power 12 is the repulsive potential, and it increases extremely fast as basically the particles start to overlap. So, this is what basically is modeling the so called, so this repulsive interaction is modeling the excluded volume interaction. What is excluded volume interaction? Basically, that two particles cannot sit, or they are not allowed to sit on top of each other, because there would be basically, if they are atoms or even they are particles, if two particles basically they exclude some volume, the two particles cannot simply sit on top of each other, electrons would repel, electron from the two atoms, they would repel the two particles away from each other, right. So, what does it say? So, at a distance less than sigma, the potential is sharply increasing, at a distance slightly more than r equal to sigma, there is an weakly attractive interaction. Well, weakly or not, it really depends upon this value epsilon, and at larger distances, if these two particles go farther and farther apart, there is a attraction, but it is very weak, the potential is nearly tending towards 0, negative, but 0. The minima of the potential, is at a value of sigma m, and you can calculate that. So, you can calculate the position of the minima. So, how do you calculate the maxima or minima of a certain function? So, here the function being V of r, basically you take dV dr equal to 0, right, and then solve for the value of r at which it is minima. So, basically dV dr equal to 0 is the condition of a maxima and minima, and later you can check that it is a minima. So, the value of sigma m comes out to be 2 to the power 1 by 6 sigma, sigma being the diameter of a particle, or sigma by 2 is the radius of a particle. So, basically where does this expression for the potential come from? So, basically sigma by r to the power 6 is the so called dispersion forces between neutral atoms. So, basically if you have neutral atoms like argon noble gas, where it has no net magnetic moment and so on and so forth, no charge and so on and so forth. So, basically what happens is that the center of the positive charge, which is the nucleus, and the electrons, they basically oscillate, they move around in space, due to which there are local in time effective dipoles which are formed, and these dipoles are constantly fluctuating. I mean, the strength of the dipoles are constantly fluctuating because basically the charges are moving around, and the center of charge of the electron cloud need not exactly match all the time. On an average, of course, it matches, but not locally. And so, basically because of this fluctuating dipoles, two atoms or particles, if you like, because Lennard-Jones is also often used to model weak attraction between larger particles. It is just a model, and it is a good model system, but it works very well for argon. Basically what you have is so when you have two atoms, because of these two fluctuating dipoles, there is a weak attraction which is induced, and which has been shown to go as sigma by r to the power 6, r to the power 6, right. And this so that is the origin of this minus sigma r to the power 6 weakly attractive term. This sigma by r to the power 12 is basically put ad hoc, and the aim is it should model the short distance extremely strong repulsion between particles, right. So that two particles do not overlap, and you see that it is increasing as r to the power 12. So, it is very fast decreasing as soon as r becomes less than sigma. If r becomes less than sigma, sigma by r is a number greater than 1, and then it sharply increases, and it increases faster than r to the power sigma by r to the power 6, right. On the other hand, when r is greater than sigma, so then sigma by r is a quantity which is less than 1, and when you take powers of small quantity, suppose 0.5 to the power square is 0.25, and then you take a power you take another power 0.5 to the power 3, and then it is 0.625 and so on and so forth, right. So, it well 25 to yeah. So, basically if you take a small number and keep on powering it, it will go slow small to smaller and smaller values. Basically, if you take 0.1 whole square, it is 0.01, 0.1 whole cube is 0.001, and so on and so forth. So, this basically dominates over this at large distances, but this dominates over this at short distances, right. So, that is what it is. Good. Now, you might have noticed that basically this point here where the potential goes to 0 is at sigma at when r equal to sigma. So, when they are just touching, and that typically is set as the unit of length in our simulations, which means that you measure all other distances in terms of this value sigma. Okay. So, that is for the Lennard-Jones. If you have a different potential, then you have to set it, you set your units suitably. I mean, here suppose you are modeling argon atoms, suppose, right, then sigma there would be a few angstroms. Now, in the computer you are not going to put in angstroms. I mean, we are not going to put 10 to the minus 10 meters as units of your simulation. You set your sigma, you say okay, the diameter of the atom is set to 1, whether it be 2 angstrom, 3 angstrom, whatever be it, you set it equal to 1, and measure all other lengths, the distance between particles in units of that. Suppose you have a box size which you can choose to be 30 sigma, 30 cross 30 cross 30 sigma, which means that the length of the box is 30 times the diameter of the particles, right. And then of course, you have x, y and z, the 3 directions, that is 30 cross 30 cross 30 sigma. And well, you can also set sigma equal to 1 nanometer if suppose you are studying some system with a particle size of 1 nanometer or 1 micron, whatever be it. So, you basically set that to be equal to 1 and measure all other distances in terms of that units. Similarly, you can set epsilon. What was epsilon? Epsilon was the unit of energy, if you remember. It is this epsilon. You set epsilon to be equal to 1, the depth of the potential equal to 1, and then measure all other energies like thermal energy kBT in units of this in units of, so say kBT equal to some number times epsilon, and you set epsilon equal to 1, and then say okay, kBT is 2. If you set epsilon equal to 1, then A equal to 2. So, the thermal energy is twice that of epsilon. By the way, one thing which I had forgotten to tell you in the previous slide is, you might have noticed that the unit of energy has been written as 4 epsilon here. So, this is the unit of energy. These numbers are of course dimensionless. Sigma is diameter by r. So, the reason you write it like this is, if you write it like this, then the depth of the potential at the minima becomes epsilon, right. Now, if you have chosen it to be as well some other quantity, suppose B. So, if you had written B here, then the depth of the potential at the minima would have been B by 4. Right. So, it is a convention that you write the expression of the Lennard-Jones in as 4 epsilon. So, that you know that the depth of the potential is epsilon, and then all other energies like thermal energy. So, if you have very low temperature, low thermal energy, then all particles would like to aggregate together because of this attractive interaction. So, this attractive energy would dominate, the potential energy would dominate over the kinetic energy, because the kinetic energy is related to kBT, right, half mv square equal to half kBT per degree of freedom. So, or half mv square, v is the speed, then v square is 3 by 2 kBT if you take the 3 degrees of freedom, right. So, that is the picture. So, that is the discussion of the starting discussion for the potential. And so, what you have, you essentially have a simulation box like this, right. I have not plotted the box fully in the third direction, the z direction. Suppose this is y, this is x, and these blue things are basically particles, Lennard-Jones. They are particles interacting by Lennard-Jones interactions, right. So, each particle, if you like, so let us focus on this particle is interacting with this particle is interacting with this particle, but this particle is also interacting with this, all other possible particles far away into the box, because this potential essentially goes to 0 only at infinity. It might have a very low value at higher distances, but still it is not 0. So, for each particle you have to calculate the potential and the force of interaction between all of the particles in the box. And similarly, if you have n particles, so n particle you have to calculate the force with n minus 1 particle, and so on so forth. It is basically n square calculation, right. So, you have n particles in a box of volume V. As I told you, we are studying canonical ensemble. We will be studying the system in a canonical ensemble, right. Now, that is a bit of a problem. Why is it a problem? Because it is extremely expensive. It's, if you have 1000 particles, then to calculate the force each time you have to do 1 million force calculations, right. Whereas, as I just told to you that basically at distances very far away, distances are much greater than sigma, 3 sigma, 4 sigma, 5 sigma. Here the value of the potential is rather weak, and even if you calculate the forces, you will see that there are very weak forces acting between the particles. So, that is not really affecting the motion. So, suppose that you had a particle here, it is interacting with another particle here, right, but the force of attraction is extremely weak. Its effect will not, I mean, it will be felt, but overall statistically it will not make much of a difference if you say that beyond a certain distance, say R c, okay, beyond a certain distance R c, say, so you say that the potential is completely 0. You set the potential completely equal to 0. So, here the strongly repulsive interaction stays, the attractive part of the interaction stays, but at R greater than R c. So, instead of this figure the Lennard-Jones, you have essentially a modified Lennard-Jones. So, that you say that you know what, the V of R beyond a certain cutoff distance R c, cutoff, that is why there is a R subscript c there, is equal to 0, it is set to 0. So, then what happens, what does it mean? So, it means that suppose there is a particle, this is a particle in question, you want to calculate the forces, the potential of interaction between this particle and all other particles in the box. So, basically all the particles which are neighboring particles which are within a distance R c given by this dashed line, they feel some force, some interaction potential, but beyond any particle which is suppose here or here, which is greater than the distance R c between this particle, feels a 0 force. So, what do you get? You get that you do not have to calculate the expression of the force and the potential for a very large number of particles. If this is your particle in question, you are calculating the force only for suppose 1, 2, 3, 4, 5 particles which are neighboring particles, and not the force between this and all the particles which are far away. So, your calculation speed, your calculation efforts, or rather the calculation effort for the computer decreases significantly, and it has been checked already by previous studies, and you can check it yourself as well, that this slight change does not affect the physics much. Similarly, if you are interested to calculate the force for suppose this red particle, all that you have to do is check out which particles are within a distance less than R c and calculate the force for only those particles, right. So, basically what you have now is that the expression for the Lennard-Jones interaction gets modified to this. So, that V of R is the standard Lennard-Jones term for R is less than equal to R c, and V r equal to 0 for all R's, for all R being the distance between two particles, distance between the centers of two particles, it is set equal to 0. So, that is very nice and good, but there is always a but and there is a problem. The problem is that basically the potential becomes discontinuous at R equal to R c. So, there is a certain potential here, a finite value of the potential here, and suddenly there is a jump and the potential goes to 0, right, because you have cut it off. Was the solution? A priori the solution looks quite simple, shift the potential up. So, that instead of having this magenta colored potential which you have also had a look at in the previous slide, you have this green curve, right, which I have just shifted up. By how much? By the value of the potential which was at this point. So, suppose the value of the potential at R equal to R c was V c. You just shift the entire potential up, you just subtract the value of V c from the entire potential, that the entire potential gets shifted up, right, and you can do your derivatives and calculate your force and so on and so forth. So, then the potential at least goes smoothly to 0 at R equal to R c, and beyond that it remains 0. So, the potential becomes a continuous function. The expression for the potential then becomes V dash R, right, because you have modified it. So, this was your original Lennard-Jones expression for the potential, and your new potential, modified Lennard-Jones potential, becomes V r minus V c for R less than equal to R c, and V dash r equal to 0 for r greater than R c. Now, this quantity is continuous, this function is continuous in the value even at r equal to R c, it smoothly goes to 0. What are the values of R c you can take? So, suppose you took R c to be 3 sigma, right, 3 times sigma. So, if you are taking sigma equal to 1, you take R c equal to 3 sigma. So, that sigma by r is 1 by 3. Then the value of V c would be 0.001. So, basically it goes very quickly to 0 at distances beyond 2 or 3 sigma. 3 sigma, the value of the potential would be 0.00137. So, you can choose the value of V c here to be this, right. You fix the cutoff right at the beginning of the code and shift the potential up. You could as well have chosen R c equal to 2.5 sigma. What would be the advantage? It is basically you have to calculate the interaction between the particle of your interest and its neighboring particles over a shorter distance. So, you will have a smaller number of neighbors over which with which to calculate, and the corresponding V c is, you can calculate it, is rather small, it is 0.004. So, the message is it goes rather quickly to 0 at these R c at r equal to 3 sigma or 2.5 sigma. You can choose your R c to be 3.5 sigma. There is nothing holy, basically you just set it, because your physics is not changing, because the potential, the shift in the potential is so low, and if at even higher distances the value of the potential would be even lower, right. So, you would think that it is quite nice, and you can go ahead and do the simulations, and in fact, if you were doing a Monte Carlo simulations, you could just work with this, where the potential smoothly goes to 0. So, if two particles are close together, they feel a repulsion. As they go farther apart, they feel some attraction, but as they go farther and farther apart, the particles, the interaction between the particles becomes weaker, and after some point at beyond r equal to R c, at r equal to R c it becomes 0, and beyond that it remains 0. Of course, as two particles are moving farther and farther apart from each other, this particle could meet some other particle which is at some other point in the box, right, and then it would feel attracted to that, and then it could come close to each other, to that other particle, it could collide with it and move apart or stick, depends upon the kinetic energy, right. But it happens that for if you are doing molecular dynamics, you have to work not with the potential. So, though I have been discussing the potential, what you actually have to work with is the force, which is minus dV dr. The expression for the force is by taking a derivative, a gradient of the potential, right. And what is the expression? If you had Lennard-Jones potential, then by taking the derivative, this is what you would get. You just take a ddr and correct for the. So, you have a minus dV dr as definition of the force, and you would get 12 sigma to the power 12 and r to the power 13 minus 6 sigma to the power 6 r to the power 7, right. So, you take a derivative, you would get a minus sign, but that this minus sign takes care of this. So, basically you again have this thing here and this thing here. Now, you have taken the potential, you have moved the potential smoothly to 0 at r equal to R c, but the thing you have to work with is not the potential, but the force, and that this function still remains discontinuous at r equal to R c. So, basically what is happening, it is two particles, as they are moving farther and farther away from each other, they are feeling some weak attractive force, and suddenly it goes to 0, right. There is a jump, there is a discontinuity in the potential. So, we have to ensure that both the potential and the force go smoothly to 0 at r equal to R c. Okay. It is not very difficult, but it will be take 10 minutes of your time, and hence we will discuss this in the next class. Thank you.